In this video, I want to introduce more formally the idea of a sampling distribution, and we're specifically going to be talking about a sampling distribution for means. In our last video, when we were talking about sampling error and things like that, we realized that a sample statistic is a random variable, and so it has a distribution. So we're going to consider means here as our sample statistic and think about what our sampling distribution for those means is going to look like. So first we'll just define what a sampling distribution is, and then we'll try and build one for some sample means, and that's going to lead us to the central limit theorem, which is one of the biggest, most important results in an introductory statistics course. And then we have a basic example to finish us out with where we can use some of the things that we're going to learn. So let's start with just answering the question, what is a sampling distribution? This is a probability distribution of a sample statistic, and it's going to be obtained from random samples that have the same sample size drawn from the same population. So we have some population, we're going to fix our sample size to be some value, maybe 5, maybe 10, maybe 30,000, who knows. And we're going to think about all of the different possible sample statistics or values of a specific sample statistic, I should say, that we could obtain from those random samples and the frequency at which we would get them. So this is kind of the way that it goes. We have some initial population that has a distribution, right? It has some sort of a construction and ways that the data is spread out among different values. And from there, we can draw a random sample that also can have a distribution, right? We can build a histogram or something like that to visualize what our sample looks like. And from there, we can calculate a sample statistic, which is just a single number. So again, this is a whole bunch of values. It can have a distribution. Our sample also has a distribution. A sample statistic is just one number. And a sampling distribution is a distribution of those single numbers. That's not how you spell numbers. Those sample statistics. So if we were to take a population, take a sample, calculate a sample statistic, and do this over and over and over again, and each time keep track of our sample statistics, we could put those sample statistics all together and get a distribution of those things. This is a little bit confusing, so I think the best way of dealing with this is to just try it. Now, there's this really great little applet online that we can look at that gives us a population here, and we'll be able to play with this in a little bit. And we are going to calculate a sample of size 5 and calculate the mean on it. So here we go. Here's our 5 observations coming from our population. This is our sample distribution, and from there we have a mean that gets placed right here. But we can do this again. We can take a new 5 values from our population, and now we have a different mean. And we can do this again. 5 new values from our population, a new mean, and again, and again. And maybe we'll do it 5 times quickly. So again, we just added 5 more sample means here, and another 5 times, and another 5 times, and another 5 times. And what we start getting is a distribution of all these sample means. Now this is for 25 different sample means, but we can really quickly just add 10,000 of these. So this just simulated 10,000 more samples, and from each of those samples, a calculated sample mean. And here is our distribution of those sample means, these 10,025 sample means that we have. And what we can notice is that with it being a distribution, we can calculate a whole bunch of stuff from it. We can get a mean and a median. We can get a standard deviation. We don't care about skew and kurtosis in this class. Skew is just the difference between the mean and the median, essentially, how far skewed left or right it is, but we're not going to care too much about that. We really care about the mean and standard deviation here. What we might notice is that this seems like it has a pretty nice shape, right? It seems like we can maybe think about the mean, 16.02, matching up with this mean. And maybe if we go ahead and click this, 100,000, wow. And we click that, now suddenly we have 100,000. Oh wait, where am I at here? Oh boy, it's hard to keep track. Yeah, 100,000, 110,025. There we go. We can just do this again and again and again and again. And now we have over 500,000 samples. And you can see what the mean of these sample means is. Remember, each of these blue bars started as 5 little observations from our population and a single mean from that getting added in. And the average of those is 16, which is also the average of our population. So that's pretty cool. So that's what a sampling distribution is. And what we care about is trying to figure out some of the ways to describe it. So the first way of describing it is to figure out the mean of the sample means. If we have a sampling distribution, what is the mean of that distribution? And so here it is. For any population, the average of all the possible sample means computed from all the possible samples of a specific sample size from the population is equal to the population mean. Sometimes what we do is we say that X bar is an unbiased estimator of mu. Now, I don't really care about that kind of language in this class because this is an introductory statistics course. But all this means is that if we redo our samples over and over and over again, we can have good confidence that X bar isn't going to be off from mu by anything more than just kind of the random chance stuff from the construction of our sample. So there's not going to be any sort of underlying structural problems with X bar. It's an unbiased estimator of mu. It's always going to be estimating mu as best as it can. It might be wrong in some specific samples, and we expect that that's going to be the case. In our last video, we saw all that stuff about sampling error and how X bar doesn't always match up with mu perfectly. But over and over again, the average of all the different possible sample means, right? This part here is the big deal. This is the one that says, okay, eventually in the long run, it'll match itself up. Cool. What about standard deviation? So let's go back, and maybe what I'll do is I'll reset this. And here we have standard deviation is 2.24 compared to 5, right? Maybe what I'll do is I'll just clear these, and I'm going to change my sample size. Maybe I'll make my sample size only 2. So now you can see we're only going to draw 2 observations. And we're going to do this over and over again, and I'll just jump up to having 10,000 of these. We can still see that we have this nice symmetry. Our mean is still, essentially 16 if I do this a couple more times. There were 750,000 trials here, and our mean is 16, just like our population mean was. But you can see our population standard deviation was 5, and here our standard deviation is smaller than that. That's kind of strange. You might also notice that when n is 2, this looks like it's a bit wider than what happened when n was 5. Here's 500,000 sample means with size n equals 5 from our sample, and our standard deviation is smaller. And what you'll notice is that if we change our sample size to 10, and we do maybe 500,000 of these again, we still are getting the right mean, but our standard deviation keeps getting smaller for this sampling distribution. So why might that be? Okay, so what we're going to notice is that if we have a bigger sample, and maybe we can just look at it this way, here comes 10 different observations now. This is going to capture a bit more of our population in the sample. And so what that means is that our sample means, our sample averages, are going to be a little bit more accurate, right? Because this is going to reflect our population a bit better. Now, not by a lot, right? But we're expecting to not get much in the tails and to get more in here. And so we're hopefully going to find that the averages are going to stick a little bit closer to 16. And we'll really see that when we bump that sample size up to 25. if I do my one little animated thing, you're going to see so many of these observations are coming from the middle of this population distribution because that's where the population lives. And so, of course, that's pushing our sample mean really close to the actual population mean. And so if we do like 5 of these, or maybe 10,000 of them, already we can see that this is looking really normal. And if we go up and do our, 500,000 or 500,000 of these, then we can see our standard deviation is actually really small now. Now, this is kind of like a variability of the sample means, right? This isn't a standard deviation of our population or anything like that. This is the variability of the actual means that we're computing. And with a larger sample size, we lose some of the variability of our sample means, which, remember, is a good thing. That's a good thing because what that means is that our sample means are going to be more accurate. They're going to be closer on average to our population mean. So all this is really good news, right? So when we talk about standard deviation, we can say, okay, this ends up being a really nice formula that we have. We're going to be looking at the standard deviation being sigma over the square root of n here, where sigma is the population standard deviation. And then for a larger value of n, we're going to end up dividing by bigger and bigger values. And so this standard deviation of our sampling distribution is going to get small. So this standard error, that's what we're going to call this thing, that's what SE stands for, is going to be based on 2 things. It's going to be based on the variability of our population. With a more variable population, that means that our sample that we construct is going to be more variable, and that means that we're going to have wildly different sample means. But also, if our sample sizes are large, we're going to notice that that is going to have an inverse effect on standard deviation of the sampling distribution. A large sample size, is going to make our standard error smaller because we're going to be capturing more of the population in our sample. And so we're going to have a more accurate sample mean. Okay, what about the shape of this? And does the shape of the population matter? This is a really cool tool that we have here, because if we clear this up, first, what we'll notice is that like when we do this, it seems like all of these distributions are pretty much normal, right? If we go to n equals 5 and we do these, we have another normal distribution with a different, standard deviation, but the same mean. But what we can do is change our population distribution. Maybe that makes sense because we have this normal distribution of our population. But if we do like a skewed distribution here, now we've suddenly got everything kind of shifted over. We can do, a 5 sample size thing. And now what we're going to notice is that our sample means are going to keep getting kind of plopped over here in the middle or on the left, because that's where things are going to be existing. And if I do this 100, 200, 300, 400, 500,000 times, then suddenly what we can see is that, hey, still our mean is matching up with the mean here. This standard deviation is still going to be matching up. It's going to be this 6.22 divided by the square root of 5. That'll work out pretty nicely. But we can see that this is approximately normal, right? Especially if we look at just the right edges of our rectangle, they're bumping right up against this normal curve. And if we do with a larger sample size, that happens again really quickly. We have a nice symmetric unimodal normal looking distribution. We have the same kind of results happening with our mean and standard deviation here. We can do a uniform distribution, which is just a perfectly flat one here, and we can do the same thing. If we our little bloop, 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 20 observations come in here, we're going to notice that our sample means are going to be all over the place. But the observations on the far left are going to kind of counteract the observations on the far right when it comes to calculating a mean. So really, these means are going to be existing right here in the middle. We have the exact same kind of relationship happening. One of the really cool things here is that you can just do like a custom distribution. So you could do like this weird like bimodal distribution here. And still, if we do this many times, this looks normal. The mean is matching up. The standard deviation is going to be the standard deviation of our population divided by the square root of our sample size. We can do all sorts of different kinds of pictures here. You can do like really flat ones with just like a spike on one side, like a real heavily skewed thing, and see what's going on. And you'll see that when we do this, there was some skewing happening. Here, let me fix this. There we go. I think that was because I didn't clear those. We get this nice normal look again. Maybe I'll clear it again, and I'll do one more picture. I don't know. What do we want to do? Maybe we'll do something that looks like... Here, I'm going to go back. There we go. I'll do something that looks like... there. And if we do 500,000 of these, our means are matching and our standard deviations are going to be the same kind of thing. This looks normal. So what the really cool result that we're going to get here is called the central limit theorem. And this thing is the thing that says for a population that's normally distributed, or as long as your sample sizes are big enough, the distribution of your sample means is approximately normal, with mean, mu, the population mean, and standard deviation, sigma over the square root of n. Population, standard deviation, maybe I'll just do SD, divided by the square root of your sample size. So this is pretty cool. We get this really nice result that says like, hey, for sample means, they're just always going to have the same type of distribution here. So here's your kind of summary here. And sorry, traditionally large enough for n, the sample size being large enough, normally means 30 or above. But what we can notice is that it doesn't actually matter that much. But we'll say that if our sample size is 30 or more, then it's fine. So here are the assumptions that we have to make. We're either going to be assuming that the population that we're thinking about is normally distributed, which we've talked about a bunch of examples of things that do have normal distributions commonly. And so that's not a hard assumption to hit. Or if not, if our sample size is big enough, we'll say 30 or more, then we can say that the central limit theorem is going to hold. And what that means is that our sampling distribution, for means specifically, is going to be distributed normally. The mean of that is mu, the population mean, and the standard deviation is sigma over the square root of n. And we'll call that thing standard error. What does this mean? What does this tell us? Well, what this does for us is it gives us a tool to get the bigger context for where a sample mean might sit in the global picture of all of the possible sample means that we might have gotten. So for instance, we can answer questions like these. This is a basic example. We're looking at sentencing lengths for federal offenses. So people convicted of federal crimes are sentenced on average to 141 months with a standard deviation of 42 months. This is not normally distributed, but we can randomly sample 100 people, and guess what? N is greater than or equal to 30, so we don't need a normal distribution. What we can do is say the distribution of sample means we are going to follow the central limit theorem here. And the distribution of sample means is going to be normal. It's going to have a mean equal to the average, 141 months, and a standard deviation, we'll call it standard error, equal to standard deviation from our population, 42, over the square root of our sample size, 100. So this is mu, this is sigma, and this is n. So what is this, 42 over 10? Or we can say 4.2. Suddenly we have the 3 key bits of information to describe this distribution, right? I can draw this. This is going to be, maybe I'll draw it poorly, but I'll still draw it. This is going to be a normal distribution here. We have this average right here at 141. And then we can draw our standard deviation lines, and we can know that those standard deviation lines are marked off by 4.2. So this is 145.2. This value up here is 149.4 if I'm doing math correctly. 141 minus 4.2 is like 136.8, I think. Yeah. And so we can keep going ahead and doing that, right? Subtract 4.2 each time. Notice our empirical rule now kicks in. And we can say if this is a real honest to goodness probability distribution, then it's not hard for us to answer questions like this. Find the probability that a sample mean is less than 120 months. We're going to randomly sample 100 people. We expect that the sample mean is right around 141. But what's the probability that it's less than 120 months? Well, this isn't hard. We have a tool for this. We could either look up like a z-score or something like that, or what we can do is go back here and say our mean is going to be 141. Our standard deviation is going to be 4.2. Let's go ahead and look this up in our little tool that we have here. Oh no, I need to reconnect this. So this is our tool that we have up on the course site. And our mean was, oh, I forget already, 141. Oh, wrong thing. Here we go. Our mean is 141. And our standard deviation, I'm not going to say it's 42. That's the standard deviation of the population. But we're going to look this up in the sampling distribution. So that one was 4.2. And now what we can do is say, well, the probability of having an average less than 120, well, that's essentially 0%. You can see down here, it's, 0.000002. So we'll say it's very, very small. So here, let me write it out. The probability that X bar now is less than 120 is approximately 1, 2, 3, 4, 5, 6, 2 something. Very, very small. Not a super likely thing. We can do a similar thing and say, okay, what's the probability that the sample mean is actually bigger than 150 months? So we'll go back here and we'll just change our value of X, which is now actually X bar. And we'll put in 150. And you can see it's a 98.4% chance that it's less than that, so a 1.61% chance that it's bigger. Or you can change this lower tail to an upper tail, and there we go. The probability that our mean, X bar, is bigger than, I wanted 150, didn't I? There we go. 150 is 1.61. So let me go write that down. 1.61%. Cool. And then we can answer questions like this that maybe seems like it's relevant. What are the range of sample means that's going to account for 95% of them? Think about why that might be a useful thing. If we want to look at reasonable sample means, maybe we'll say, like, what's a range that almost all of them are going to fit in? Well, this one we could just do by hand, right? The empirical rule says that 95% of the stuff is going to be within two, I'm going to call them standard errors now. And so this is really going to be 141 plus or minus 2 times 4.2, because our standard error is 4.2. And so we've got 141 plus or minus 8.4. 141 plus 8.4, that's 149.4. And 141 minus 8.4 is 132.6, I think. And so this is a range of sample means that we would expect 95% of the time our sample averages are going to be within these values. All of this, I think, is really helpful. The central limit theorem is a wonderful tool because not only does it tell us that our sample mean is going to reflect the population mean and that we can get standard deviation out of it, but we get this normality of the sampling distribution, which allows us to answer a ton of different questions. Because once we know the shape, center, and spread of that sampling distribution, we have every bit of information that we could need to answer all of these different types of probability questions. So this is really great. If we wanted to look this up on our little tool that we have here, what we'll do is we'll go back into this find percentile or quantile thing. And instead of a lower tail, I'm going to go two-tailed, and we'll use this 95% probability. And here's the exact values that we have. The empirical rule that we used was a rough estimate, because we know that it's not actually 2 standard deviations. It's like 1.96 standard deviations or something like that, or standard errors in this case. But here's your range. 95% of the stuff is going to be between 132.768 and 149.232. So this is pretty cool, I think. This gives us a really nice way of getting everything that we might really need out of this with just a little bit of information. Remember, the assumptions that we were making was either that the population was normally distributed, it was not the case here, or the sample size is large enough. And that is normally going to be the case. We're going to have decent sample sizes in a ton of different things that we look at.